Welcome to Data Science 1, Probability, Central Limit Theorem, Part 1. Okay, some things we're going to need to remember: normal distributions, independent, identically distributed, sample mean, and the properties of the sample mean from the last video. And here they are. So IID means independent, identically distributed, which means they come from the same population, they elicit the same distribution, and that one does not influence the other anyway from a probabilistic standpoint. We found that the sample mean has the mean of the random variable, which should be the mean of the population if we've taken our sample in a random fashion, and we can measure the variability around the mean using sigma squared over n. So wait, hold on a second. Aren't the mean and variance measures of center and spread? Isn't that how we describe distributions? Well, what if we could find the shape as well, or at least come close, okay? So let's do a little simulation here. I want to see what happens when we change our sample size. So we're going to suppose x1 through xn, or IID f of x, has expected value of x is mu, and the variance of x is sigma squared. I'm going to drop the x and the y on the mu and the sigma squared right now because we know they're the same number and they're on the same random variable. Here we're going to let f of x be the uniform distribution from 0 to 1. So we want to look at what does the shape of the histogram of the sample mean look like if we ran 1,000 simulations with the sample size equal to 1. Well, this is what it would look like, and look, it's exactly what you would think it would look like. It's pretty uniform. Because a sample size of 1, the sample mean is just going to be that data point. So if I did it 1,000 times, this should be just 1,000 observations from a uniform 0, 1. Now, what we're going to do is we're going to add some things to this picture to make it easier to look at. So I've added a green line here that is the actual theoretical mean of this. Okay, so we want to know, okay, what's the theoretical mean for a uniform 0, 1? In this case, it's a half. I'm laying on top of this a normal distribution, and you will see why here in a minute, but right now it kind of falls off the picture, so don't really worry about it right now, but we'll use it for visual reference later. And this dashed purple line is the actual mean of the sample means. So we want to see if that gets anywhere close to the actual theoretical mean. Okay, so this is our setup. What happens when we go to n equals 2? Oh, wow. Look at the drastic change here. Notice that we went from flat to something that's triangular. The ends came way down. These sides came way down. And if you looked at it, you go, wow, the uniform or the normal distribution fits well. And no, it doesn't, because this is actually a triangular distribution. When n equals 3, it looks like this. N equals 4, n equals 5, n equals 10, n equals 20. Now, notice what's happened here. We've gone from something that went from 0 to 1, and look at the huge gap here. It's really squeezing down around the mean, and that's exactly what that sigma squared over n says it should do. Okay, so quick summary here, because I'm trying to keep this video short, because we're going to do a part 2. Looks like the histogram of the sample mean across the samples becomes approximately normal, right? The bell shape did do reasonably well on it, with the mean mu and variance sigma squared, which are the underlying population parameters. The underlying distribution didn't need to be normal, right? Because we used uniform. We knew it wasn't normal. The only thing we need is for n to be large enough and for mu and sigma squared to exist. Now, the question for part 2 becomes, does this work for discrete distributions? Look, the uniform is continuous, so maybe it should work there. But what about discrete distributions? That's what we'll take up in the next video. See you there.